I want to go over the last three types of reactions. I don't know if we'll get to all of it, but I'll try. Definitely single and double replacement, and then the only last one is combustion, which should be pretty straightforward. So starting with single placement reactions, this one will probably take the most time. This is when you have one element that replaces another element in a compound. So the general formula is going to be A plus BX yields AX plus B. Now, the key, come on, admit, there we go. You remember I told you last week that there's clues to being able to identify which reaction is which type, because that is the ultimate goal, is that I can give you an equation and you can identify what kind of reaction it is, and also be able to predict products at the end. So first thing is, the big giveaway is having a single element by itself plus another compound. So if you see an element that's by itself plus a compound, you're going to have to decide whether it's single replacement or whether or not a reaction will happen. Now, in this kind of reaction, it's possible that a reaction will not happen because it's completely based on the activity or the reactivity of that single element. I mentioned last week about active metals and reactive elements, and I'll go over that again. I'll go over that again today when I show you the activity series in a second. So there's a list of elements, particularly metals, that go in order of increasing reactivity. And so the way that you look at it is every element that is higher is more active, and so it will be able to replace any element that's below it in the series. And you use that activity series to determine one, if there's a reaction, and two, what the products will be. So the most common single replacement reaction is with metals replacing another metal. So for example, aluminum is a more active metal than lead. So if lead is in a compound with, say, oxygen, and aluminum is by itself, then aluminum can replace or displace, which is why sometimes you see it called a single displacement reaction, but it's the same thing. So when solid aluminum is placed in an aqueous lead-2 solution, when you put solid aluminum in aqueous lead-2 nitrate, the aluminum replaces the lead because it's a more active metal. So you would see that, hold on. Do I have the reaction for that? Oh, in the next slide. Okay. So again, if you analyze the first half of this equation, you have a single element plus a compound. So that is a dead giveaway for a single replacement reaction. So the first thing you're going to have to do is think about the activity series and think about if aluminum is going to replace lead. If, like, let's just look at this for an example. So first you have to find aluminum, which is here, and where's lead? Lead is down here. So because aluminum is above lead, it means that it will replace it. Aluminum will replace lead. So that means that the aluminum kicks out the lead and you get aluminum nitrate and lead by itself. This is why, again, it's important to write formulas correctly. So you're not just going to look at the NO3 2 and say, okay, then it must be Al NO3 2. No, you have to look at the ions. So aluminum is +3, NO3 is -1. So you take the 3, cross it down here, Al bracket, NO3 bracket 3. So that's basically it. You just have to look at the activity series. Now we're going to be doing a lot of practice, so you'll get used to it, but the general rule of thumb, as I said before, looking at a periodic table, group 1 are going to be the most active metals, followed by group 2, and then you get transition metals towards the top of the what do you call it? The top of the I can't talk. The top of the transition metal block will be more active than the bottom ones. Pay special attention to where hydrogen is. And then, as I said last week, silver, platinum, and gold are all expensive metals because they're unreactive. So you should not have to remember that at all. But maybe copper and mercury would be good to remember, that copper and mercury will not replace hydrogen. So the metals are the most common. The halogens have their own activity series, but it's really quite easy because this is exactly the order. Oops, not FL. This is exactly the order they are on the periodic table. So if you always have a periodic table available to you. So just know that fluorine replaces any of the other halogens. Chlorine will replace bromine and iodine, and bromine can replace iodine only. Iodine will not replace any other halogen. And like I said, we'll do lots of practice. And nothing. No, lots of practice. Okay, so if you have ever seen the reaction of sodium and sodium metal in water, sodium is an active enough metal that it actually replaces one of the hydrogens in water, and you form sodium hydroxide. Also remember, from the synthesis reactions, I talked about that as well. So we got aqueous, and that's a gas. So when you put, we didn't have a chance to do it because we've been online so much this year. But normally I will show you this as a chemical reaction and then ask you to justify why it's a chemical reaction. When you see it, actually, I can show you. Let me find, I might as well find it on YouTube. I'm sure you've seen it before, but stupid bars in the way. Okay. Oh, there you go. Sodium metal and water. I got to go back and share screen. New share. No. All right, so we're just going to show like a giant chunk of sodium in a pond. I guess we're going to kill a bunch of fish.
This is a demonstration video showing some of the chemical characteristics of sodium metal, along with some of the chemical reactions of sodium and sodium-based compounds. Sodium metal is typically stored in the mineral oil, as sodium metal would react with the humidity in the atmosphere. And unlike most metals...
Okay, so what he just said is that sodium has to be stored in mineral oil because it's so reactive that it will start reacting with the moisture in the air.
Sodium is relatively soft, so it can be cut with a scalpel, as shown here. You wouldn't be able to cut a block of iron as easily as this. When the sodium metal is cut, you can see a shiny metallic surface is exposed. The shiny surface created will rapidly tarnish in air due to the humidity, then form a dull surface. Since sodium metal is reactive, the first set of experiments we're going to perform, we're only going to use a small amount of sodium metal. The larger pieces of sodium metal we're going to store back under the mineral oil until we're going to experiment with those later. The first chemical reaction we're going to look at is sodium metal reacting with water. We measured the initial pH of the water and found it to be around 6. Now we drop in some sodium metal and immediately you can see a reaction.
So the gas that's being released is hydrogen gas. The sodium metal is replacing, there you go, sodium metals replacing the hydrogen in the water. So what you're left with, if you replace one hydrogen from H2O, you're still left with hydroxide OH.
Once all the sodium metal is reacted, we've measured the pH of the liquid again, and this time it is alkaline.
Way up at 14.
With a pH of 14. This is due to the formation of a solution of sodium hydroxide. Let's put a larger piece in and light the hydrogen. See the characteristic yellow flame of sodium? We'll try an even larger piece towards the end of the video. More sodium metal was reacted with the water to form a stronger solution of sodium hydroxide, and now we're going to have a look at some of the chemical characteristics of sodium hydroxide solution. To start with, we're going to pipette a small amount of our concentrated sodium hydroxide onto some aluminium foil, and you can see a reaction where the sodium hydroxide is reacting with the aluminium to form aluminium aluminate and hydrogen gas. In our next demonstration, we're going to see the chemical reaction between solutions of copper sulfate and concentrated sodium hydroxide.
Oh, I'll come back to that because this is going to be double replacement. So I will come back to that, but I might as well watch him dump it in the pond, right? Did they do that? Oh, here.
With the larger blocks of sodium metal, to do this experiment, we ventured outside rather than to conduct this experiment within the workshop. We set the cameras up and chucked a rather large block of sodium metal into a lake of water, and after a few moments we have an upscaled reaction of what we saw in the workshop.
And a lot of dead fish.
Thanks for watching.
Okay, let's go back. So that's an example of a single replacement reaction because sodium is such an active metal. It replaces. Sorry.
Warning. Sodium is a highly reactive and
No. My computer's kind of slow. What am I doing? Oh yeah. Go back here. Okay, there we go. Oof, too many screens open. Okay. So single replacement, a less active metal than sodium may still react with water, but it has to be at higher temperatures. So maybe steam. But I'm not really so concerned that you remember metals that don't react with cold water, but react with steam. That's a bit too much actually. Okay. Now, more active metals can react with certain acidic solutions to replace the hydrogen as well. So what's going to happen here is that you're going to have a metal compound, which is called a salt, and hydrogen gas. For example, magnesium is quite high in the activity series. So it is going to replace the hydrogen in the hydrochloric acid. And so you're going to get the metal plus the non-metal. That's magnesium chloride. This is a salt and hydrogen gas. Now, salt is a group of compounds that can be formed through the reaction with acids, whether it's an acid-base reaction or it's a metal replacement reaction. For some reason, I don't know why we called NaCl like the name salt, because then that's like a specific name of a specific compound that is in a group of many other types of salts. So this is the reaction here. So that's the magnesium ribbon that you see. And in hydrochloric acid, you see the bubbles because the hydrogen is being replaced. Now the halogens can replace each other. Fluorine, as I said, is the most reactive. Super easy because you'll always have access to a periodic table through homework, test, quiz, whatever. And all you have to do is literally look at group 17, and that is your activity series. So the ones on the top are more reactive than the ones on the bottom. Fluorine will replace any other halogen. So in this example, we have chlorine. Again, for each of these, you see that there are single elements by themselves in a reaction with a compound. And that is the key, because this is A plus BX. And the key to this is identifying, it's a single replacement reaction. So therefore I have to access the activity series to determine whether or not a reaction will occur. Speaking of whether or not a reaction will occur, you see for the third one, there is no reaction because bromine is below chlorine in the periodic table. So it will not replace it. It's not more active than chlorine. So if you have a metal or a halogen that's lower in the activity series, it will not replace a metal or a halogen that's higher in the activity series. So let's do some practice. These are all single replacements, so you just have to predict what the products will be based on the activity series. Actually, instead of doing that, I've got a better worksheet where you've got the activity series right next to it. So let's do this and that. Yeah, I don't really know why you're not. Okay. Then I will share it through AirPlay since you're being picky and weird. Screen mirroring, zoom, there we go. There we go. All right, so I've got the work. Wait, why can't you see my split screen? What? Really? You guys are only seeing, you're not seeing the split screen, right?
Yeah.
Oh, I thought I was so clever. That doesn't work. Okay, hold on. Let me try something else. Okay. Okay. Ooh. Oh, you can see it now, right?
Yep.
Okay, just got to use the cable then. All right, so I've got the activity series on the right-hand side, so you can access that. It has a lot more metals in it than the previous one did. So I just wanted to go through these together with you so we can practice using the activity series. So for the first one, again, the big clue is you see a single element all by itself with a compound. And then that should tell you single replacement. We have to compare these two metals. So you have to be able to identify, don't forget that a metal replaces a metal. For number 2, you see it's halogen. So don't think that chlorine is going to replace sodium. Chlorine is a halogen. It may or may not replace iodine, but we'll do that in a second. So looking at the activity series on the right-hand side, and I can't like move my mouse on it or anything, but we find aluminium is the second one in the yellow section. And lead is the last one in the yellow section. So aluminum is higher than lead, which means it will replace it, which means you have aluminum, which is +3, and you have nitrate, which is -1. So the formula is going to be AlNO3 3 and Pb by itself. And that will be a solid, obviously, because it's a metal. And the last thing you want to do is balance the equation. It's a bit thick of a line. So you want to balance the equation. Remember what I said, you balance polyatomic ions as a whole unit as long as it's on both sides in the same way. On the left, I've got 2 nitrates. On the right, I have 3. So I'm going to do that shortcut where I just swap the 2 and the 3. So they're each 6. So 3 goes there, 2 goes here, and you leave the single elements by themselves because they're easy to balance. So aluminum has to be 2, lead has to be 3. Okay, for the second one, we're looking at chlorine. Chlorine, oh, I don't have that in my, okay, let's go here. So periodic table, because that can be my activity series. Okay. So there's your activity series for the halogens. Fluorine is above iodine, which means it will replace it. Wait, what was I doing? What am I doing? Bleh. Okay, we're looking at chlorine and iodine. Bruh. Chlorine is still above iodine, so it will still replace it. So you're going to have sodium and chlorine together. So you're going to have NaCl. Don't forget, it's replacing the iodine, which is the non-metal, so it will come in second. The metal always comes first in a compound. Chlorine is -1, sodium is +1, or you just realize that I is in the same group as Cl, so they're going to have the same charge, which means the formula for NaCl, or sorry, the formula for sodium chloride is going to be in the same ratio as sodium iodide, because they're all in the same group, which means they have the same number of valence electrons. And then the remaining species is going to be iodine, which is a halogen, which means it's diatomic. So you have to have 2 of them. Remember, it's HNO and all of the halogens, diatomic, so they have to be in pairs. Final thing, you have to balance. It should be obvious from Cl2 and I2 that you need 2 NaI and 2 NaCl. Next is chromium plus water. So whenever you have a metal plus water, you're going to look at if the metal is going to replace the hydrogen. There we go. My brain is really running on empty today. All right, so we go to the activity series and we see chromium is right about the middle of the yellow section, in between zinc and iron. You see hydrogen is all the way down just before lead. So because chromium is above hydrogen in the activity series, it will replace it. Now here's where it gets tricky, because on the periodic table, not this one, but on the one that I have, chromium has 3 different possible charges, 2, 3, and 6. So you're going to form chromium hydroxide because it's going to replace one of the hydrogens, not both. Okay, that's important to remember. It replaces one of the hydrogens, not both. It is up to you which of the 3 charges you would like to use for chromium, because there's no indication here of which one it would be. I tend to go with the first one, or whichever one will make the formula the easiest for me. So I'm going to go with chromium 2. And what we're going to have left here is hydroxide, which is -1. So my formula is going to be chromium hydroxide CrOH2 to balance. And then, of course, you have H2 gas because it's replacing hydrogen. Don't forget, just because chromium replaces one of the hydrogen in H2O, that doesn't mean that one of your products is just H. H doesn't exist. Okay, it's not a thing. If you're like, is that a thing? No, it's not a thing. H2, that's a thing. That's hydrogen. So the last thing you want to do is balance your equation. So I'm going to start with CrOH2, and I see that there are 2 oxygen atoms, so I needed 2 in front of H2O. That means there are 4 hydrogens. There's also 4 hydrogens on the right-hand side because we have 2 here and 2 here. So we are balanced. Next is Fe plus silver acetate. So we're looking at iron versus silver. You should not even have to look at the activity series for this because silver is what? Silver is expensive. Why is silver expensive? Because it is not reactive. So it's going to be at the bottom of the list. Iron is around the middle of the list, right? It's almost exactly in the middle, or it is exactly in the middle of that yellow section. So it absolutely will replace silver. Again, Iron is a transition metal. It has more than one charge. It is totally up to you which of those charges you use. The possible charges are 2 or 3. I'm going to pick 2. And then we have acetate, which is -1. This is why it is desperately important for you to remember your polyatomic ions. I think actually, maybe Wednesday we'll go over polyatomic ions. Maybe I'll make a quiz. Should I do that? Let me think about it. I'll let you know tomorrow. But tentatively, there will be a polyatomic ion quiz on Wednesday. We'll see. Okay, so my formula for iron 2 acetate is going to be Fe, because the metal comes first, C2H3O2 bracket 2, and Ag. The last thing we do is balance. So we need 2 acetates, which means we need 2 silvers. Next, lead plus tin 2 hydroxide. So we need to find lead, we need to find tin. If I look at the periodic table, I look at the activity series of metals, and I see that tin is just above lead, which means lead is not going to replace the tin in tin hydroxide. So you write NR for no reaction. Nothing happens. If lead is not more active than tin, it will not be able to kick tin out of that compound. So literally nothing happens. I'm going to go back to deal with double replacement. Here we go. Double replacement, in my opinion, is the easiest of the 5 types of reactions because of the type of equation that you see. In a double replacement reaction, you have ions of 2 compounds. That's a key. 2 compounds that exchange places in an aqueous solution to form 2 new compounds. So the general formula AX plus BY yields AY plus BX. You're literally going to pick 2 of the ions and just swap them. That's it. So the key is if you've got 2 compounds. So far we haven't had that, okay? We have had, what's a good color? We've had A plus X yields AX, not 2 compounds. It might be 1 element and a compound, like a metal plus water, but it's not 2 compounds. We've had AX yields A plus X, definitely not 2 compounds. And we've had A plus BX yields AX plus B, again, as a reactant, not 2 compounds. So this should be really easy to identify. And then you pick either the A and the B to swap, or you pick the X and the Y to swap. Because they're compounds, the A and B are going to be positive, X and Y are going to be negative. So positive and negative are the ones that have to go together. Just switch them around. A really good example of double replacement is called a precipitation reaction. And this is one of my favorite things to do in the lab. And hopefully we can go back to school next week. And this is like the one time where you, well, no, actually the 2 times, because we get to do it twice. You get to kind of play with chemicals in the lab. So a precipitate happens when you have 2 solutions, which you can see here, both aqueous. 2 solutions that when you mix them together, they form something that cannot dissolve in water. And it's really cool to see because you have 2, what look like 2 liquids. And when you mix them, it's like magic, like a solid forms. So weird. Some of them, like lead iodide, have a color. This is bright, like sunny yellow. Don't know if I have a picture of it or not. No, guess not. Oh no, there it is. Ta-da! So you can see you've got a clear solution from the top beaker. You've got a clear solution in the bottom beaker, and this bright yellow insoluble solid form is called a precipitate. Okay, not to be confused with precipitation, which is like rain and snow and hail and things. We could actually do this in the lab if we were in school, because I have both potassium iodide and lead nitrate. But alas, another option for double replacement is the formation of a gas. For example, if we have iron 2 sulfide plus 2 hydrochloric acid, we get hydrogen sulfide, which is a gas. This is actually the worst smelling gas in the history of gases. It's like worse than the worst fart you've ever smelled, because it smells exactly like rotten eggs, and it's actually poisonous. I worked with it occasionally in my first job at a university in the lab, and you absolutely have to keep it under the vacuum hood. It's like, we don't have it at school, but in proper labs, you have what's called a fumigation hood. So it's like this little chamber that you do your experiments in that has a fan running that sucks any kind of fumes or smoke or anything like that. It sucks it right up, so it doesn't come out into the room. But even when I had, I think I worked with it like only 2 times because it's so dangerous. Even with the, what do you call it? I'll show you a picture, because I don't know I don't know what to call it. It's like the window that you pull down. Fumigation hood. Yeah, okay. I'll show you this thing. Yeah, so these guys. So you do your experiment inside there. And even with this thing pulled like all the way down so that like my little arms were just kind of in there with my hands trying to manipulate it, the whole lab still smelled like rotten eggs. That's hydrogen sulfide. Anyway, that is a gas. So when you have a reaction like this, it's still double replacement because you've got 2 compounds. So you can have the iron and the hydrogen swap places, or if you prefer, have the sulfur and the chlorine trade places. Either way, the iron's going to go with chlorine and the hydrogen goes with sulfur. Again, because of charges, hydrogen is +1, sulfur is -2. That's why it's H2S. And again, with iron, it can be iron +2 or iron +3. Here you can see that because it's with sulfur and it's in a 1-to-1 ratio, we know that sulfur is -2. That means iron has to be +2 because it's a 1-to-1. So that's why it's FeCl2. Also things to pay attention to. So there's a lot of things that I've taught you, and because I've taught most of it online, I feel like 70% of it hasn't really been absorbed permanently. I feel like it's absorbed during the lesson, maybe for the homework, but then after that, it's like, boop, gone. So that's why we need to practice, because now we're in the thick of concepts in chemistry where you're really starting to use a lot of the things I've already taught you, and you have to be able to do it, which is why I stressed you have to remember your polyatomic ions. You have to remember how to write formulas for ionic compounds to make sure that the charge is balanced. And we can practice all of that. If you guys are like, yeah, we'd like to go back and practice some of that, we can spend as many classes as you want going through worksheet after worksheet if you want. It's totally up to you. But just make sure you let me know if you feel like you're not confident in that, and then I can help you practice with that. Otherwise, I will just keep going and going and going like the Energizer Bunny. In some double replacement reactions, water is formed. So in this, this is called a neutralization reaction. Neutralization reaction. What time is it? Make sure I don't go over time. Ooh, okay, got a couple minutes. Again, you've got a compound plus a compound. So in this case, the sodium is going to go with the chlorine. The hydrogen is going to go with the hydroxide. Or you can just say that you swap, you just swap hydrogen and sodium. So you get sodium chloride. And when you put hydrogen together with hydroxide, you get water. And water is always a liquid, unless otherwise stated, maybe it's steam or something like that. Okay, and then the last thing, just to round off this topic, and of course, we're going to do lots of practice, combustion reaction. Now, combustion is burning, and so the key to combustion is this guy right here. If you have anything plus O2, it's combustion. Here's another key. If you have hydrocarbons, hydrocarbons are compounds that have carbon and hydrogen only. They are going to burn to produce two very specific compounds, carbon dioxide and water. These are going to be your products every single time, as long as the other reactant besides water, besides oxygen, is a hydrocarbon. So if you see CH4, I can't write, C3H10, anything like that, if it's just carbon and hydrogen plus oxygen, your products are carbon dioxide and water. So here is a hydrogen, or sorry, this is a balloon full of hydrogen, and they use the little candle to make it go boom. That's combustion. Okay.